This video is about the Pythagorean Theorem, and going through this video will help you in investigations 3 and 4 and you're looking for Pythagoras' book. The Pythagorean Theorem involves right triangles. It only works for right triangles, so any other kinds of triangles this formula will not apply. Take for example this right triangle outlined in blue. One leg of the triangle has a length of 3. The other leg has a length of 4. The Pythagorean theorem is a relationship between the squares of these legs and the squares of the hypotenuse of that triangle. So in red, we have the area of those squares. The area of a 3 by 3 square is 9. If I take the other leg and I make a square out of its length, it would be a 4 by 4 square, and it would have an area of 16. Now what we discovered over time is that if I take the hypotenuse, and I don't know the length of that hypotenuse right now, that's the long side, and I'll put a little question mark by it. But if I make a square out of it, we found that over and over the area of that square is the sum of the two squares made by the legs of that triangle. So for example, this one would be an area of 9 plus 16, or 25 square units. Now we can verify the area of that large square, the square that's made by the side of the hypotenuse, by breaking that tilted square into pieces and adding those pieces together. So for example, if I break this into a triangle, the triangle has a base of 3 and a height of 4, and the area of a triangle is found by base times height divided by 2. So that'd be 3 times 4, or 12, divided by 2 is 6 square units. Now I can do the same thing right here and make another triangle that has the same area. 4 by 3 divided by 2 is 6. And I can do another one right here that has the same area, and another one right here that has the same area, and then 1 square unit left on the inside, and you'll notice that that has a total of 25 square units. Okay. And we also know that if a square has the area of 25 square units, and the side length is the square root of that area, or the square root of 25. That happens to be a perfect square, so the square root of 25 ends up a nice even 5. And so all 4 sides of that large square are 5. We got a 5 here, a 5 here, 5 there, and a 5 there. And you notice that that side of the square is the same length as the hypotenuse of my original triangle. So remember, this was an area of 9, that small square. This one had an area of 16, and this large square had an area of 9 plus 16, or a total of 25, and we just verified that that big square had an area of 25. So if we look down below on this sheet, I made a square that has an area of 25, which is a 5 by 5 square. We just found that that square up above, let me come back to it here, on a tilt still has a side length of 5. So down below, I've redrawn that square. We know this side is 5 and this side is 5 and it has an area of 25. Now what you'll notice is that I could put one of those squares from up above, the 4 by 4 square, inside of that area of 25. And then if I broke the other smaller square up, it has an area of 9. We'd have 3 square units here, we got 3 square units here, and we got 1, 2, 3 square units there. So the 9 square would fit around the edges of that for a total of 25. Now from that comes the idea of the Pythagorean theorem. If we call the small sides of the triangle, the legs, A and B, so we'll call this one A, we'll call this one B, and the long side, or the hypotenuse, C, then if you remember back to what we already did, was first we squared the side A. So if we write that as A squared, or A times A, then we squared B. So if you write that as B squared, or B times B, And we added those together, those areas, and we got the area of the square of the hypotenuse. And if that's called C, that area would be C squared. So now if we put our measurements of this triangle into this formula, we'll see that it works for every right triangle. A was 3 units and B was 4 units, and we found that C was 5 units. So if I put 3 in for A, and I square that, and I put 4 in for B, and I square that, I should get 5 squared, or C squared. 3 squared is 9, 4 squared is 16, 5 squared is 25, and when we add 9 and 16 together, we do get 25, so that this verifies the Pythagorean theorem works for this case. So the Pythagorean theorem shows us the relationship between the legs and the hypotenuse of a right triangle. And one of the things it's most useful for is to find the missing side length of a right triangle. So for example, if I had a 2 by 1, 2, 3, 4, 5 right triangle, so I'll write 2 and 5 here, then I can put those numbers into the Pythagorean theorem and find this unknown side of the hypotenuse of the triangle. So if we go back to our Pythagorean theorem, a squared plus b squared always equals c squared for right triangles. If the small side is 2, we'd take 2 squared, and the other leg is 5, so we'd say 5 squared, and we know together they have to equal c squared. 2 squared is 4, and 5 squared is 25, and that equals c squared. 4 plus 25 is 29, so c squared is 29. But c itself is the square root of 29 if you take the square root of both sides to maintain equality. So if we squared this leg and got a 2 by 2, we'd get 4. Squared this one, we'd get 5 by 5, or 25. And if you add those areas together, you should get the area of this large square on the hypotenuse, 4 plus 25 being 29. And if I know that area, then I know the side length of that square, which is the same as this hypotenuse, or the square root of 29. The Pythagorean theorem is also useful to find the missing leg length of a triangle if we know the hypotenuse. For example, if we had a right triangle that was 7 on one leg, we didn't know the other leg, but we did know the hypotenuse, we could still use the Pythagorean theorem to find that out. So if we go back to our Pythagorean theorem, a squared plus b squared equals c squared. This time we don't know a. We're going to call this side the question mark side a. We know 7 is for the leg is b, and 10 is the hypotenuse, or c. So for a, we're going to leave that a squared for now, and we're going to put in 7 for the side length, the leg length, and we know that the hypotenuse, or c, is 10. So you have a squared plus 7 squared equals 10 squared. So if we simplify, we get a squared plus 49, or 7 squared, is 100, or 10 squared. Now we essentially have an equation that we need to solve for a. So we subtract 49 from both sides, we maintain equality, and we get a squared equals 51. So I know that the area of a square is 51. So the side length is the square root of that. So again, to maintain equality, I take the square root of both sides, and a is the square root of 51, and that's an exact answer. So over here on the leg A, I can write the square root of 51, which is exactly how long that side is. But we probably want to know about what that side length is of that triangle. So the square root of 51 on a calculator comes out about 7.14, etc., etc., etc. So we know it's a little bit longer than 7. We also know that that's a pretty good approximation because 49 is a perfect square, and the square root of that is 7, and the next perfect square up is 64, and the square root of that is 8. And if we put the square root of 51 in between 49 and 64, it's a little closer, it's actually quite a bit closer to 49, so it should be pretty close to 7, just a little bit bigger than 7, which is what our estimate on our calculator gives us.